Let's do some more physics problems from Chapter 1. Let's do numbers 8, 16, 26, 35, 45, and 49. These are by units, mostly just converting units. That's a thing we need to be able to do so we can communicate with other humans who might not be using the same units as us. All right. So, just in case, just a reminder, if you have not yet done this assignment, you need to complete this assignment to the very best of your ability before you watch this video. You know what's not allowed? I can monitor this better, of course, if we have real in-person school. But you can't say, oh, number 8, read that, nope, don't know what to do. Number 16, going to go on and do that. No, sorry. You need to attempt, even if you really don't, you feel pretty unconfident, you still need to make some attempt and have something to show for your attempt. Not, I don't know how to do it. Because we're big kids now. Let's see. This is a fun problem. Harvard Bridge, which connects MIT with its fraternities across the Charles River, has a length of 364.4 smoots plus an ear. The unit of one smoot is based on the length of Oliver Reed Smoot, Jr., class of 1962, who was carried or dragged length by length across the bridge so that the other pledge members of the Lambda Chi Alpha fraternity could mark off, with paint, one smoot lengths across the bridge. The marks have been repainted biannually by fraternity pledges since the initial measurement, usually during times of traffic congestion so that the police cannot easily interfere. Presumably the police were originally upset because the smoot is not an SI base unit, and the Massachusetts police, they're definitely all in on the SI units. But these days they seem to have accepted the unit. So there's a little chart here that gives us some conversion factors, and they want us to what do they want us to do? Where's the actual question? Oh, here we go. What is the length of 50 smoots? I'll just say S. How about that? 50 smoots. They want us to turn that into willies and Zeldas. So let's see. The conversion factor, if I have 50 smoots and I want to convert to willies. Well, looking at the little chart here, drag my book over here, it looks like that 212, the zeros match up here, so 212 smoots is the same as 258 willies. Oh. 258 willies, same as 212 smoots. Okay? And that'll do for that conversion. Now with the other one, on the other hand, I've had many students trip up on this part here. Here, the 32 and the 60 are matching up. So let's see, this is from here to here is the same, right? So from here to here in smoots, that's 180 smoots is the same as, looks like 156 Zeldas, right? From 60 to 216, because those are the things that match up, right? So the distance from here to here is the same as the distance from here to here. So that's 180 smoots is 156 Zeldas. So 180 smoots, same as 156 Zeldas. And then you can multiply those out and find that the answers should be that this is about let's see. Oh, I did this one upside down. Sorry. My smoots aren't going to cancel there, are they? So flip that over and then multiply, and then you should get the right answer of about 60.8 willies, and here you should get about 43.3. I don't know why I put a extra decimal point there. That's weird. It's not allowed. Only one decimal point per number, please. All right. Number 16. Time standards are now based on atomic clocks. A promising second standard is based on pulsars, which are rotating neutron stars. And some rotate at a rate that is highly stable, sending out a radio beacon that sweeps briefly across the Earth once with each rotation, like a lighthouse beacon. So pulsar PSR 1937 plus 21 is an example. It rotates once every one rotation every 1.557 yada yada yada, plus or minus 3 milliseconds, where the trailing plus or minus 3 indicates the uncertainty in the last decimal place. In other words, it doesn't mean plus or minus 3 milliseconds. It means plus or minus 3 in the very last decimal place that they have reported. So I guess I better write that whole thing. 806 448 872 75 plus or minus 3. So the milliseconds here, that's indicating it's about 1.5 milliseconds, right? But with this much precision, and the plus or minus 3 is how much wiggle room we have there, right? So how much deeper into that number are we? I'm going to count in groups of 3. So like we're 1 milliseconds is 10 to the negative third, right? So this would be 10 to the negative 6, 10 to the negative 9, 10 to the negative 12, 10 to the negative 15, 16, 17. So we're talking about plus or minus 3 times 10 to the negative 17 seconds. That's the wiggle room there. That might help us answer the question in a minute, or questions. Let's see. How many rotations does this star make in 7 days? All right, that's just a straight up conversion. So 7 days, is that what they said? 7 days. Let's see. We know that in 7 days there are in 1 day there's 86,400 seconds, and this is in milliseconds. So I'm going to go from seconds to milliseconds, and I did that the wrong way around. If I want to go from seconds to milliseconds, then this is where the 10 to the negative 3 should be, because the milli and the 10 to the negative 3 are equal to each other. And then I have this 1.557, etc., times 10, or that's milliseconds, and that's 1 rotation. So there's my conversion chain there, and multiply that all out, and I should get that it makes about 3.88 times 10 to the 8th rotations. All right, how about part B for number 16? How much time does it take the pulsar to how much time does it take to rotate exactly 1 million times? So that's 1 million rotations, and in 1 rotation we have this much time passes, 5, 5, 7, etc., times, or that's, I guess we could just say that's milliseconds. right? So let's see. If you want to multiply that out, you can do that with your calculator, I suppose. It's just going to move this decimal over 6 places because I'm multiplying by 10 to the 6. And that was milliseconds. So then if I move it back the other way to get regular seconds, it's about 1,557 point yada yada yada, all that stuff, seconds. They also want to know what is the error there. Well, if this is how much error there is for one rotation, then for a million rotations, there's a million times this is the wiggle room. So that would just be plus or minus 3 times 10 to the negative 11 seconds. Right? Cool. All right, 26. I think we're moving on to length now. No, just kidding. Mass. Number 26, we have 1 cubic centimeter of a typical I like this one too. The typical cumulus cloud contains 50 to 500 drops of water. Okay, so 1 cubic centimeter contains 50 to 500 drops. So that's like a conversion factor for us. In the context of this problem, those two things are equal. Because we've got a range of 50 to 500, which have a typical radius. So one drop has a radius of a drop is about 10 micrometers, which is 1 times 10 to the negative 5th meters. Okay? For that range, give the lower value and higher value for each of the following. So in part A, they want to know how many cubic centimeters of water are in a cylindrical cumulus cloud of height 3 kilometers and radius 1 kilometer. So it's 3 kilometers high, and it has a radius of 1 kilometer. And we're approximating this cloud as like a cylindrical shape. Okay, these are these storm clouds that we see around here in the summertime that just puff up real high and have a lot of water in them. So let's see. I think the first thing we need to do is figure out what the volume of this cloud is. So the volume of this cloud is a cylinder. Well, a cylinder is the kind of shape where you have a base and then it's got a height. So the area of the base times the height. So that's pi r squared. So that's pi times 1 kilometer squared times the height. And I don't know why I wrote that all way up there. So that's going to be 3 pi cubic kilometers. So, I'm just estimating here. These are just rough estimates. So 3 times pi, 3 times 3 and change is about 10-ish. So that's about 10 cubic kilometers. I think for the purposes of our estimating here, that should do just fine. Okay, that's the volume of a cloud. So if I can turn that if I can get that, let's see, maybe I need to know what the volume of a drop is. So the volume of a drop, I know the radius, and I know that the volume of a sphere, I wonder if you know that off the top of your head. That might be one you need to look up, but it does come up fairly regular-like. I'll make a little note here. Volume of a sphere is 4/3 pi r cubed. So here for this drop, I've got 4/3 times pi, which is about 4. I'm just estimating here. And that's times the radius cubed. Right, so that's actually 10 to the negative 15. So let's say 4 times 10 to the negative 15 cubic meters. That's the volume of a drop, right? Okay, so it looks like I can get to, what do we want here? We want the, how many cubic meters of water? Okay, so I've got a conversion factor here that says the volume of one drop is this. So let's see if we can do that. So I want to get from kilometers to meters. There's 1,000. That's what that K means. But I need to cube those. Okay, so that gets me to cubic meters. And I want to know how many drops. Well, I've got a conversion factor here. So actually, it looks like I need to get to cubic the volume of a drop. Yeah, I think I can go straight to this, can't I? What do they want to know the number of drops? No, they want to know how many cubic meters of water. Oh, so I'm already there. Right, so I don't know, why am I fussing with this? So how many cubic meters of water are there? I think we're done with part A, aren't we? So that's about 2. Why do they have a 2 there? In the book they have 2 times 10 to the third for their range. Why are they getting that 2? Just think about this for 1 sec. Oh, because this is, I'm sorry, I know what I'm doing here. Or rather, I guess what I'm not doing. This is just how many cubic meters there are in here. They want to know how many cubic meters of water. So we need to get back to the water stuff here. Let's see. We do have quite a bit more work to do here. So let's reinstate that line. All right. So I know that in here we've got 1, let's get to cubic centimeters. So here I need to go from meters to centimeters. That's 10 to the negative 2. Need to cube those. All right, and then I know that 1 cubic centimeter has, I'm going to do the 50 drop version, and then I'll just multiply the answer by 10 to get the range of them, to get the 50 to 500. So let's say we're doing for 50 drops here, and then I'm going to move my chain down here. I know that 1 drop has a volume of about 4 times 10 to the negative 15 cubic meters. And that is water. So I think I'm good there. Let me just check, make sure that my chain gives me an answer that agrees with the book. So I've got 10 times 1,000 cubed Divide. Are you one of these people that hits enter after every single calculation? Can we stop doing that, please? So this is 10 to the negative 2 cubed. That's divided by 10 to the negative 6. And then times 50. And then times 4 times 10 to, that should be a 15 there, sorry. Times 10 to the negative 15. I think that's good. 2,000. So 2,000 cubic meters. And then the range, if I had done 500 drops, that would have given me another 0 on there. So there's my range. 2,000 to 20,000 cubic meters of water. All right. Now, what else do we want to know? How many 1-liter pop bottles would that fill? So let's see. What's 1 liter? That might be one we need to look. 1 liter is 1,000 centiliter. That's no 100 centiliters, of course. 1,000 milliliters, because that's what those words mean. Let me flip to the back here and see if we can get a conversion factor. So I'm going back to that. Let's see. For volume, this is on page A6, the appendices in the back of your book. 1 liter. So yeah, that's right. It is just, sorry, I was thinking we just needed to push that decimal point around. For part B here, 1 cubic meter is equal to 1,000 liters. That's what that is. And I guess the thing that I was thinking about, that 1 cubic centimeter is equal to 1 milliliter? I think that's true. You can check that out, but we don't need that. We actually need this. So if we have 2,000 cubic meters of, well, each one of those cubic meters is 1,000 liters. And are we talking about 1 liter pop bottles? Who calls it pop? Soda bottles. But usually they come in 2 liter bottles, so I don't know why they're asking us about this 1 liter bottle. I guess in England, these guys are a little bit Anglophilic. So that just means that there's going to be, multiply these by 1,000. That's all. You can write out the conversions if you want, but it looks like 2 million to 20 million British soda bottles. Right, 2 million to 20 million. And then part C of this one, we've got water has a density of 1,000 kilograms per cubic meters. We actually saw that in another problem, didn't we? How much mass does the water in the cloud have? Okay, so if we know how many cubic meters, then we have 2,000 cubic meters, and I know that water has a density of 1 cubic meter is 1,000 kilograms. So it looks like I'm going to get the same answers. I'm just multiplying by 1,000 again. So that would be 2 times 10 to the 6 kilograms, and then with the range, if we were using the 500 drops, so we get 2 million to 20 million kilograms of water in the cloud. That's a lot. All right. Let's see. Where are we now? On 35. See if I can fit it down here. Number 35, we have an Old English children's rhyme states, Little Miss Muffet sat in a tuffet, eating her curds and whey, when along came a spider who sat down beside her. and frightened Miss Muffet away, I think is the last line, isn't it? The spider sat down not because of the curds and whey, but because Miss Muffet had a stash of 11 tuffets of dried flies. The volume measure of a tuffet, one tuffet is equal to 2 pecks, which is equal to half, oops, I think I need some more paper on here. Punched right through one of those holes. Which is equal to half an imperial bushel, which is equal to, oh, and there we're done. So 1 imperial, oh, is equal to, sorry, not quite done, is equal to 36.3687 liters. All right, so what was Miss Muffet's stash in pecks, imperial bushels, and liters? So she has, we're starting with 11 tuffets. So oops, that's an H, not an 11. 11 tuffets. And in part A, we're converting to pecks. So 1 tuffet is 2 pecks. So 22 pecks. All right. 5, you can start with there if you want, 22 pecks, 1 peck, oh sorry, 2 pecks is equal to 1/2 an imperial bushel. So that's 5.5 of those. And then last, what about in liters? So 5.5 imperial bushels. Well, one of those, 1 IB, is 36.3687 liters. So keeping 2 sig figs is about 200 liters. All right. Get another piece of paper here. Did I run out? Nope, I got one more. I should do it. For, what are my last two? 45 and 49. 45. We have a unit of time sometimes used in microscopic physics is the shake. And 1 shake is equal to 10 to the negative 8 seconds. That's a billionth of a second is a nanosecond. So that's 10 nanoseconds, if you want. Are there more shakes in a second than there are seconds in a year? Okay. How many shakes are there in a second, and how many seconds are there in a year? So let's see. How many shakes are there in 1 second? So if I want to turn 1 second into shakes, so that's just a matter of turning that number over, really. So there's 10 to the 8 shakes in 1 second, and then we're comparing that to, this is part A, how many seconds are there in a year? So 1 year is, let's see, 1 year is 365 days. If that you can put 365.25 days if you want, to count for leap years, but it's going to be good enough. And 1 day is 86,400 seconds. There it is again. So that gets me to seconds. How many seconds are in a year? So 365 times 86,400 is about 3.15 times 10 to the 367 times 10 to the 7th seconds in a year. So there's more shakes in a second. It's pretty close, but this is 10 to the 8th, this is 10 to the 7th. So close, close. But more shakes in a second. For part B, let's see, what are we doing for part B? There it is. Humans have existed for about 10 to the 6 years, whereas the universe is about 10 to the 10th years old. So humans about 1,000,000 years, and the universe is about 10 billion. It's really about 14, more like 14 billion, but that's a good estimate, nearest power of 10. If the age of the universe is defined as one universe day, where a universe day consists of universe seconds, as a normal day consists of normal seconds, how many universe seconds have humans existed? Okay, that's kind of confusing. So what they're saying is this. So let's say here's the age of the universe, approximately. And let's say that this is, we're going to call this one universe day. So like if the universe was like a whole, like the age of the universe from Big Bang to now is like a universe day. Then what if you took that and you divided it up into universe seconds? So how many universe seconds are there in a universe day? They're saying that a universe day is divided up into the same number of seconds. So that's our same 86,400. So one universe second is this number chopped up into 1/86,400th of this. So I'm going to take that 10 to the 10th, and I'm going to divide it up into 86,400 pieces. And so one universe second is about about that many years. Okay, I think we're good so far. Humans have existed for about 10 million years. If the age of the universe, how many universe seconds have humans existed? So humans have existed for about 10 to the 6, about 1,000,000 years. And this is one universe second. So if I do that math, it's about 8.64, and you can see where that's coming from here. Universe seconds. Okay, so I mean, I think that's kind of a cool problem, and it's kind of fun to think about, but you got to take a step back to understand what this means. So that's like saying if the whole universe, the age of the universe is like a day, right? Like, because a day is something we're very familiar with, right? In time, like seconds and hours, things like that, minutes, we're familiar with that. So if the age of the universe was laid out like a whole day, humans have existed for 8.64 seconds out of that whole day. So in other words, that's just like I think we're supposed to take away from that problem as well. That's a pretty short amount of time for the whole age of the universe, like a whole day, and humans have existed for 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,005, 1,006, 1,007, 1,008, 1,000, about that much of a whole day. So when I was just counting there, like that amount of time out of this whole 24-hour period that you're watching this video in. That's what that's about. Fun to think about. And I do not know why I wrote a C here, because there's no part C of that problem. So moving on, last one, which is number 49. Traditional unit of length in Japan is the ken. and 1 Ken is equal to 1.97 meters. What's the ratio of square Kens to square meters? Cubic Kens, cubic meters, the volume of a cylindrical water tank with blah, blah, blah. Okay, let's crank out A and B first. So what's the ratio of square Kens to square meters? So I would like to know what is the ratio of a square Ken to a square meter. So that ratio is equal to, these are equal to each other, so 1 square Ken let's see. So actually, let's do this. Let's convert this and say, so 1 square Ken is equal to, I would just need to square that number, 1.97 squared. That's 3.88 square meters. So the ratio, if I want to know what this ratio is a pure number, like a 4-to-1 ratio or whatever, then I need to have the same units. So 1 square Ken is equal to 3.88 square meters, and 1 square meter is 1 square meter, so then I have the same units, so it's the ratio is 3.88. You could say 3.88 to 1, but 3.88 is the same thing. Okay, so part B, we want to know cubic Kens to cubic meters. So 1 cubic Ken is equal, since 1 is equal to 1, that would be 1.97 cubed, 7.65 if I round that way, and same deal, that's going to be my ratio. 7.65 is that ratio. And then part C, let's see, we've got a volume of a cylindrical water tank that's a height of 5.50 Kens, and it's got a radius of 3 Kens. Okay, so the volume of this thing in cubic Kens is pi r squared h, no square there, and that is going to be pi r squared h. So the volume of this thing is about 156 cubic Kens. And in part C, they want to know, oh, that is part C. They want to know that. So 156 cubic Kens. And in part D, what do they want in cubic meters? Okay, so we can do that conversion. I know what the conversion factor is now because I did it right here. So 156 cubic Kens. 1 cubic Ken is equal to 7.65 cubic meters. So 156 times 7.65, so that's about 1.19 if I'm keeping 3. Oops, times 10 to the 3rd cubic meters if I'm keeping 3 sig figs. There it is. 40 minutes of physics fun.